Hello everyone, we are Group 2 of TMF2234 operating system. Our group consists of 4 persons which are me, Freda, Lieu, Boon, Ooi Lee Chen and Voo Wan Qian. Now let us proceed to the introduction. Round-robin scheduling is primarily intended to be used in time-sharing system. It incorporates preemption, allowing the system to switch between processes. Round-robin scheduling assigns each task an equal share of the CPU time. Tasks are placed in a circular queue, and when a task allocated CPU time expired, it is moved to the back of the queue and a new task are added to the front.
Thank you, Freda. Hi, I'm Ooi Lee Chen. Now I'm going to execute the C++ program. Okay, as you can see here, this is the main menu for the programs. Users are required to choose whether to start the program or to exit the programs. After we start the programs, we are required to enter the quantum times in order to start the round-robin scheduling algorithm. Let's say if we enter 15. After we enter the quantum times, a list of performance metrics for the job list appear in a table form. The performance metrics we have is completion times, turnaround times, waiting times, context switch times, and number of interrupts for each job. Now, below the table, we have the calculation of average turnaround time, average waiting times, total context switching, and the total waiting times. This calculation will provide us the data we need for analysis and evaluation of round-robin algorithm method. Okay, that's all from me. Thank you. I'll pass the next part to my member, Lily.
Hi, I'm Lily. For this part, I'm gonna show you the result of our project. Move on to the table. It shows the comparison of different quantum time used by round-robin scheduling program. All of the jobs were scheduled by using various quantum time, as you can see in the table here. There are 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, and 60. I'm not going to read out the result, but here, I would conclude that as the quantum time increases, obviously, the total context switching decreases and the total number of interrupts also decreases. Well, as you see, the average turnaround time and average waiting time is not decreasing along as the quantum time is increasing. The average turnaround time rises and drops simultaneously after quantum time 30, and also the average waiting time is different after 30. Okay, let's hear the analysis and recommendation part from Wan Qian. Thank you.
For the analysis and recommendation part, we have used the chart to compare the data of the average turnaround time, average waiting time, total context switching, and total number of interrupts with different quantum time. When we compare these 4 data, we can see that quantum time 40 has the lowest average turnaround time and the lowest average waiting time. For the total context switching and the total number of interrupts, quantum time 40 is not the lowest value, but it considers the low number in aggregate. Therefore, we choose 40 as the most appropriate quantum time for our job list. This is because it has the lowest average turnaround time and average waiting time. It is also has a lower value for the total context switching and total number of interrupts. The performance of the round-robin scheduling is highly dependent on the quantum time. When the quantum time is too small, the overhead will occur, resulting in the significant number of the context switch. So when the quantum time is high, scheduler will become the first come first serve algorithm.
In conclusion, based on the result, it is recommended to use quantum time of 40 for the job list. However, the result might change when the program evaluates different job lists and result in change of recommendation for quantum time. In short, the program only evaluates the performance of the round-robin scheduling algorithm and provide data, but does not provide the best quantum time. That's all from us. Thank you.